In this section of chapter 11, we will discuss about Melanic ester, Aldol condensation reaction, Claisen condensation reactions. Now, first I'm going to go over Melanic ester reaction. So this is Melanic ester, CH2, COO, CH2, CH32. So there are two of these group in this compound. And structurally, it is shown here. Now in this case, there are two acidic hydrogens. I can identify this to you. These are the two acidic hydrogen. And one of them would leave in presence of a strong base like this. This is strong base, Na plus CH3CH2O minus. So that's sodium ethoxide. So sodium ethoxide, you can think about ethanol. Ethanol, when you get rid of hydrogen, you get ethoxide, and with sodium plus, it gives sodium ethoxide. That's the strong base. So this is a strong base. And in presence of that strong base, alpha hydrogen gets out. In other words, this strong base reacts with alpha hydrogen, which is an acidic hydrogen. So initially you get a negatively charged carbon. That negatively charged carbon is attracted to alkyl group, the carbon atom of alkyl group. If you think about a compound like this, C, H, 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 Br, obviously Br will be negative, carbon will be positive. So this carbon with electron pair will be attaching to that carbon, Br would leave, and that's how you get the final product. Now, let me show you rest of the reaction in next slide. Now, in last slide, I have shown you how alkyl group gets bonded where acidic hydrogen was. Like in this case, this R came from alkyl halide. So if you have methyl group here, say R prime, R is CH3Br, then obviously this would be CH3. Now, I have one more acidic hydrogen in this compound. This is alkylated Melanic ester. Again, same thing can happen. In presence of a strong base, this hydrogen would be gone, and then you would have an electron pair on this carbon. Let me draw this with a different pen color. So you'd have an electron pair on the carbon when hydrogen leaves. So this is electron pair. And that electron pair, it can react with alkyl halide where Br would leave, and you finally get two alkyl groups attached to carbon. I want to emphasize that this part of this compound comes from Melanic ester. So after hydrolysis and H3O plus, everything else leaves. Carbon dioxide is given off. Most of ethyl alcohol is given off. And then this is the final product you're going to get with two alkyl groups attached to carbon and COOH. Let me go over problem number 9. That would show you how you can synthesize a compound by using Melanic ester synthesis method. So let me first write down question 9b, page 384. So that's 9b. You have a benzene ring, double bond, single bond, double bond, single bond, double bond. So that's benzene ring. Then you have CH2, then CH2, C double bond O, OH. Now, question is, how do I synthesize this compound by applying Melanic ester synthesis method? Here I mentioned to you that COOH part comes from malonic ester. So this part is coming from malonic ester, and rest would be coming from alkyl halide. So accordingly, I can write down alkyl halide right away. So I'm going to use a pen, the blue pen, for showing you the alkyl halide, CH2, and then I need to write down one alkyl group. A good living group is a bromine, so I'm going to use Br as an alkyl halide. And I know that this part eventually would come from malonic ester. So obviously I can write down now malonic ester in presence of a strong base. So a strong base could be sodium ethoxide. So in the book they probably wrote down like this, CH2. I'm going to write down the malonic ester now. There are two ester groups, C double bond O, C2H5, which is same as CH2CH3. So you'd have C double bond O. In book they often write down just ET. It means ethyl group. That way you don't need to worry about this big group. But since this is the first problem I'm doing by using malonic ester from the homework, and I'm showing the whole thing. But if you want, you can abbreviate this to ET, is the ethyl group. So in presence of sodium ethoxide, now I'm going to write down as ET. Again, that's easier to write down. And ethanol, ETOH, as solvent. Again, you already know the mechanism. That means these two hydrogens that you have, both are acidic, because this is the alpha location from each of these C double bond O group. So we have two C double bond O group of malonic ester, and this Br eventually is going to leave, and there'll be bond formation between this carbon and this carbon, and during heating process in last step carbon dioxide would leave, and then finally you get this product. So key thing in solving this kind of problem is to find out what part is coming from malonic ester and what part is coming from alkyl halide, and then just add malonic ester and alkyl halide in presence of sodium ethoxide in ethanol, and that would finally lead you to the desired product formation. Now we talk about aldol condensation reaction. In aldol condensation, you use aldehyde or ketone and combine them together, again in presence of a strong base. This is a strong base, sodium ethoxide. So ethoxide, basically sodium is plus and ethoxide is minus. I mean, it's a pretty strong base. So that's going to remove acidic hydrogen from one of these aldehydes in this example. So that's why you got CH2 minus here instead of CH3. So the original compound here, let me write down the original compound. So these two CH, that's CH3, and then you have C double bond OH. Now these are, let me highlight this with blue. These are acidic hydrogen, and sodium ethoxide is going to take up that hydrogen, and you find that's how you get CH2 minus. When it is CH2 minus is attracted to positively charged carbon, or it's called nucleophile, and that's why this arrow is shown from here to here, showing that that electron pair on carbon that gives it the negative charge is attracted to that carbon, and then carbon breaks this double bond or the weaker pi bond, that's what you see here, and you finally get O minus, and which picks up hydrogen, so you finally get this. OH. So that's beta hydroxy, because this is carbonyl group. You have alpha location, you have CH2, and beta location, you have OH. When you combine these two molecules together, make sure you practice yourself. So in aldol condensation, we get beta hydroxy ketone or beta hydroxy aldehyde. So remember what beta location is. The carbon adjacent to C double bond O is alpha. Next carbon would be called beta, and that beta location you have OH. So this is how you get aldol condensation product. We already discussed that as a result of aldol condensation, you're going to get beta hydroxy aldehyde when you begin with aldehyde, or beta hydroxy ketone when you begin with a ketone. And they can undergo dehydration reaction when you heat it. So in presence of heat, so when you are heating it, you're going to get the kind of products called enone products. To be more exact, enone actually you get from ketone, because ene stands for alkene group, one for ketone group. But for aldehyde, you get enal. But in general, we call them enone products. By going over problem number 14, we'll discuss how exactly you can get enone products. Let's go over problem number 14 from page 388. Now, the question is, write the structure of enone products you would obtain from aldol condensation of the following compounds. So I'm going to do 14A. This is a pentagonal ring with C double bond O group. So cyclopentanone, that's basically, it's a cyclic group. And in aldol condensation reaction, two of these molecules are going to react together. So I'm going to write down a little differently this one so that you can see those bonding rather quite easily. So I'm going to write down with this orientation. Keep in mind, each of these have alpha hydrogen on each side. So I'm just showing you one side, not to complicate this. And in presence of a strong base, hydrogen will be gone, and you get a negatively charged compound. Say this one changes to, I'm going to show you one additional step here. This is double bond O, and now since it's acidic, one of the hydrogens would be gone when it reacts with, say, strong base like sodium hydroxide in ethanol. So when it becomes minus, so this is minus, is going to react with carbonyl carbon. This is the carbonyl carbon. Let's use a different color of the pen. So that's delta plus, and this is delta minus. So this electron pair will be attracted to that carbonyl carbon, and that releases like this. So let me show you. So this is in presence of a strong base like sodium hydroxide in ethanol. So let me write down in presence of sodium hydroxide. So in presence of sodium hydroxide. Remember, you need a strong base so that it can remove hydrogen as H+, the acidic hydrogen, from alpha location. This is the alpha location. So once they combine, it will look like this. This is the double bond. It's alpha location. This carbon is going to be bonded to the next group. So let me draw it like this, and O becomes O minus, and that picks up hydrogen, and you get OH. And don't forget that we also have one hydrogen here. And let's use a different pen so that this is more clear. So this is nothing but the combined product of two ketone group, in this case ketone, with a cyclopentanone. Now again, this is hydroxy ketone. Now we are going to show you how the dehydration takes place. So your experimental condition is such that this hydrogen OH group would be leaving as H2O. How do I know they're going to leave? In the question that they'll tell you that, just like in this particular question, that write down the structure of enone products that you would obtain from aldol condensation. Enone product means dehydration would happen. That's how you would have a double bond. En group is coming after dehydration. Dehydration means removal of H2O. And we're showing you now the final product. So let's change. Okay, so pentagonal ring, double bond, and now you have a double bond in here, and you'd have so this is the final product you get. This is the enone product that you can get from beta hydroxy ketone. And this is a very typical reaction, and you can try the other problems yourself. Claisen condensation reaction happens between two molecules of esters, and that's what we're showing you here. Again, idea is the same. From alpha location, this is the alpha location, this is carbonyl group. Since this hydrogen attached to the alpha carbon is acidic, in presence of a strong base like sodium ethoxide, this hydrogen will be gone from alpha position and it becomes minus with pair of electron. Let's show you with pair of electron. And that pair of electron is attracted to positively charged carbon because of the fact oxygen pulls the electron away from carbon. So whenever this carbon, alpha carbon of second molecule, makes a bond with carbon of the other molecule, and then this double bond, weaker pi bond, has to break, and it's going to leave its electron pair onto the oxygen, and that's what would be the first step of the reaction you need to think about. And eventually C double bond O, when it makes the double bond, it gets rid of CH2 CH3 group, and we're going to show that in next slide. Now here, that's what you had in previous slide, and this electron pair you try to make is double bond. Again, in order to maintain 4 bonds around carbon, these groups OCH to CH3 will have to be expelled, and it goes back to the solution, and then you end up with this product after you add H3O plus. So this is basically beta keto ester. So in Claisen condensation, you get beta keto ester. Here I'm going to explain to you how to do problem number 11.8. So problem number 8, chapter 11. So let me write down that. This is 11.8. Asking for resonance structures. The question is, draw 3 resonance forms of the most stable enolate ion you'd obtain by deprotonation of methyl 3-oxo-butanoate. So let me first draw the structure. CH3, then C double bond O. Then I'm going to write down CH2 a little differently so that I can explain it well. Then you would have C double bond O, O, CH3. So in presence of a strong base, so I just write down in presence of a strong base, acidic hydrogen. Let me highlight that with, this is the acidic hydrogen, and we have 2 such hydrogens. One of them would be gone, and that would give rise to what we call enolate ion. So let me just draw that. CH3, C double bond O. No, I have only 1 hydrogen left. So let's write down that hydrogen. Only 1 hydrogen, and I have a pair of electron. So this is the pair of electron, and this hydrogen from previous step, C double bond O, O, CH3. Now there should be negative charge here, and we already know how to assign those charges by counting electrons on carbon. There are 2 electrons solely on carbon, then 3 electrons are coming from the shared bond, the 5, and neutral carbon should have 4 valence electrons. That means it has 1 extra electron. You can also think it this way, same conclusion you can get, that hydrogen leaves as H+, so it leaves behind its own electron onto carbon. So carbon got an extra electron from hydrogen, and that's why it's minus. So this is the first of our resonance structures. Since we need to draw 3 structures, the double arrow is shown for resonance structures. Let me show you with a different pen color so that you know the movement of electron. This electron could be moved either to the right or to the left. So if it moves to the right, it goes in here, then the carbon where it goes to would have too many bonds, so it will have to break its weaker bond and leave its electron pair onto oxygen. So this would give rise to this structure, CH3, C double bond O, and then you'd have CH double bond C O minus OCH3. So look at here, originally the charge was on carbon, now it moved to oxygen, and that's pretty favored because of the fact oxygen is more electronegative, so it would love to have that negative charge on it. So this is going to be our structure number 2. In order to get the third structure, you need to work on molecule 1 or resonance structure 1. So I'm going to get the third one from here. Now let me use a different color so that you don't get confused here. Now I'm trying to generate the third resonance structures by moving electron pair to the left like this. Now this time, again, the double bond that carbon has to break. It has to break its weaker bond and leave its electron pair onto oxygen. So that would give rise to the third resonance structure. So it's going to look like this. CH3, CO minus, then you'd have a double bond here, CH, this is minus here, and you'd have C double bond O, CH3. Let me double check whether everything we wrote down correctly, because we often make mistakes. So this is the double bond giving CO, single bond COOCH3. So I think it's right. So let's label it as 3. So these are the 3 resonance structures that they're asking for. So hopefully you do it yourself to understand how to write down resonance structures.